In the last session, we have covered different types of load and stresses and their examples. In this section, we will cover other important parameters which are required for design of machine. On screen, you are watching stress strain diagram for ductile material. In designing various parts of machine, it is necessary to know different properties of materials. The mechanical properties are commonly determined from standard tensile test carried out on universal testing machine, which is known as UTM. All of you are very well observed this test in your strength of material course. The result values of stress strain are used to draw this diagram. Therefore, this diagram is known as stress strain diagram. From this stress strain diagram, the first characteristics, that is proportional limit, which is shown from O to A. As we say, OA is a straight line. This represents stress is proportional to strain. Material behaves as per Hooke's law. This property of material is known as proportional limit of material. Second, elastic limit. It must be noted that even if load is removed beyond point A up to B, the material will regain its shape and size. This means the material has elastic property up to B. Thus, it is known as elastic limit of material. Let us see third stage, that is called plastic stage, which is shown from B to C. If material is stressed beyond B, the plastic stage will reach. That is, even load is removed, the material will not be able to recover its original size and shape. Then, material behaves like plastic. Hence, this stage is known as plastic stage. Yield point. At point C, material yields before applying the load, and there is sufficient strain without increasing the stress. Therefore, stress at point C is known as upper yield stress, whereas stress at D is known as lower yield stress. It is an important property of material. Next characteristic, ultimate strength. If the stress goes on increasing to its maximum value up to point E, at E the stress which attains its maximum value, which is known as ultimate stress. Ultimate stress or ultimate strength is another important property of material. Next one, breaking stress or breaking failure. It is a stress at which the material actually breaks or tear out. Thus, this stress is known as breaking stress. Let us see another stress strain diagram. This stress strain diagram is of brittle material. The behavior of brittle material between O to A is similar to ductile material, and it obeys Hooke's law. Therefore, this range from O to A is known as proportional limit. The main difference between ductile and brittle material is that in brittle material, plastic formation doesn't appear and material gets fractured without plastic deformation. Therefore, yielding is not possible in brittle material. Therefore, the maximum stress attained at point B is the ultimate strength of brittle material. Ultimate strength is the important property for determining dimensions of different components during design. Let us see a rotating beam of circular cross section and carries a load W. This load induces stress on the beam which is cyclic in nature. That is, if A is under compression, at the same time the point B is under tension. After half revolution, B will be under compression and A will be under tension. This variation of stress depends on speed of the beam. Therefore, the stresses which vary from one value of compressive to the same value of tensile or vice versa are known as completely reversed or cyclic stresses. If the material is subjected to repeated stress, it gets fail below the yield stress of material. Such failure is known as fatigue failure. Fatigue failure mainly depends on 1. Size of component, 2. Magnitude of static or fluctuating load, 3. Number of load reversals. As shown in the figure, if the stress is below certain value, as shown in dotted line, the material will not fail, whatever may be the number of cycles. The stress is known as endurance limit or fatigue limit. There are many cases when machine members are subjected to combined stresses, that is tensile, compressive, shear. In shafts or C-frames, there are direct tensile or compressive stresses due to force and shear stress due to torsion. In crankshaft, there are both torsion and bending stresses. In such cases, maximum principal stresses due to combination of tension, compression and shear may be considered. Maximum values can be calculated by giving these principal stress equations. As we studied in the previous section, the strength of machine element is based on mechanical properties. Properties are generally determined from simple tension, compression test or prediction of failure subjected to axial stress only. But the components subjected to biaxial or multi-axial stresses, prediction becomes complicated. Therefore, to solve these problems, different theories have been formulated. The first theory, maximum principal stress theory. According to this theory, the failure occurs at a point in a member when maximum principal stress reaches to its maximum value. The theory based on failure in tension and compression ignoring shear stress. Therefore, it is not applicable for ductile material. This theory is generally used for brittle material because brittle materials are strong in shear but with in tension and compression. Second theory, that is maximum shear stress theory. According to this theory, failure occurs at a point in a member when maximum shear stress in a biaxial system reaches value equal to its yield point. This theory is generally used for ductile material. The third theory, named as maximum distortion energy theory. Maximum distortion energy is the difference between total strain energy and strain energy due to uniform stresses. According to this theory, failure occurs at yield point when the distortion strain energy per volume in multi-axial system reaches to its maximum value. This theory is generally used for ductile material.